let's find the local extrema of this function p of x, 2x to the fifth minus 4x to the fourth, and then we'll try to sketch a graph just by using the information that the first and second derivatives give us. So this is just a polynomial function, easy peasy. Use the power rule on each piece to find the derivative. And then to find the critical values, we're going to set it equal to 0 and then solve for x. Okay, well, before we do anything, it looks like there's a common factor of x cubed, and actually both of those numbers are even, so I'm going to go ahead and factor out a factor of 2. So we're left with 5x minus 8 when we factor out 2x cubed. And so that means that our critical values, the spots where the derivative is 0, are at 0, right? If x is 0, then x cubed is 0, so that'll satisfy the equation. But also at 8 over 5. That's the x value that makes that second term in the factorization 0. So we have our two critical values, and now we're going to use the second derivative test to determine if they're local maxima, local minima, or we need more information. If you can find a formula for the second derivative pretty easily, that's usually the way to go. The first derivative test can be useful sometimes, more useful than the second derivative test, but if you can compute a formula for the second derivative no problem, like in this example, then there's really not much point in using the first derivative test. It's better to use the second derivative test. Okay, so we need to evaluate the second derivative at these critical values. We need to see whether they're positive or negative there. Well, 0 is super easy, right? If we plug in x equals 0, it'll be 0 on both of those spots, so p prime prime, second derivative at 0, is just 0. Oh no, oh, shoot. When the second derivative is 0, there's no information from the second derivative test. Shucks. So we'll have to get back to that, see exactly what we can do. But let's go ahead and plug into the other critical value into the function. Okay, so if we do 40 times 8 over 5 cubed, so we'll end up getting that value. That's a positive number. Okay, that means by the second derivative test that the function, that being a positive value, it has a local minimum at this critical value. Okay, and now remember how we couldn't get any information at 0? What are we going to do to reason this through? So we can make a little sketch of what's going on. If this is an imaginary x-axis, here's 0, here's 8 over 5, and we know we have a local min there, right? So the function's going to be decreasing and then increasing. So we know that the first derivative will be negative here, corresponding to that increase, positive here, corresponding, or I said we know that the first derivative will be negative here, corresponding to this decrease, positive here, corresponding to this increase. We don't really know what's happening here, but if we just test one value out here, we're sort of combining the first and second derivative tests here, we'll be able to figure out what's going on. Okay, so what is p prime of minus 1? Minus 1 is a perfectly good number to test in there. So that's the first derivative, not the second derivative. So we're plugging in negative 1 into the first derivative. Okay, 4 wrongs make a right, but 3 wrongs make a wrong. That's a minus sign. But there's that final minus sign, so we get 10 plus 16, that's 26. That is positive. So in fact, just by that test, we can see that the function is increasing, and it actually does have a local maximum at 0. And that's cool. The second derivative test didn't give us any information at 0, right? Because the second derivative is 0. If you plug in 0 here, you'll get 0. But going back to the first derivative test, we were able to determine what was happening. So p of x does have a local max at x equals 0. Here, I'll show you just a quick little sketch of this function so that you'll believe me. we found our two critical values to be 0 and 8 over 5. What this function looks like is that it's coming up and then it really flattens out at 0 like this, and then it dives down and has a local minimum at 8/5, but it's a little bit kind of shallower or thinner, in terms of the peak there. That's this function that we've been studying, 2x to the 5th minus 4x to the 4th. So let's classify our critical values as we did algebraically before, just on the picture I mean. So we determined that at 8/5 it's a local minimum, and at 0 it's a local maximum. So here's our local minimum, and here is our local maximum. Awesome. Okay, what about the inflection points? The spots where it changes from being concave up to concave down or vice versa. There's actually only one, it's right there. So that'll be an inflection point in this graph. And that's because that inflection point is a spot where the function changes from being concave down, right, we're pointed downwards there, to concave up. In the last example, we had the situation where we had found a critical value to a function, somewhere where the derivative is 0, and then we had tried to apply the second derivative test, but when we plugged in, we got 0 for the second derivative as well. So what's going on? What is happening when the first and the second derivative are both 0? Notice if the second derivative is 0, then you can say that this point is a critical value not for the original function, but for the first derivative. Sort of cute, right? Because the second derivative is the derivative of the first derivative. What this says is that this is a critical value for the first derivative. Okay, so what is going on in this situation? Let's just think about it for a second. And I'm going to split up into these 4 cases depending on the behavior of the first derivative, whether the first derivative is positive or negative, i.e. whether the function is increasing or decreasing. So in the first scenario, the function is increasing and then it levels out sort of so flat that both the first derivative and the second derivative vanish. So in this situation, we will have a local maximum. We have a critical value at C. It's a red dot. And then we'll circle it in gold because it's a local maximum. Okay, the second situation is just kind of the analog where you're decreasing, but then it levels off so flat that both the first derivative and the second derivative vanish. That'll be a local minimum there at our critical point at C. You can see that just from the shape, right? Or you can see it from the first derivative test, right? First derivative test says changing from positive to negative first derivative is a local max, or changing from negative to positive first derivative is a local min. What about these other 2 situations? If the first derivative is positive the whole time except for this one spot where you have a critical value, then the graph's going to look like this. Okay? Well, that's a situation where you have a critical value, but it's not a local max or local min. So we kind of are revisiting that shape. That's what's happening when the first and second derivative are both 0, and we're getting an inflection point there, circled in purple. And then the other case is the same thing, but in reverse. You're decreasing, you flatten out so that the first and the second derivative are 0, and you'll have an inflection point at that critical value instead of a local maximum or a local minimum. So those are the 4 possibilities for when both the first derivative and the second derivative are 0. Okay, now we're going to fill in a similar sort of table. Each entry in the table is a possible behavior of the graph depending on whether the first and second derivative are equal, less than, or bigger than 0. So all possible, that's why I'm using these curly brackets. You can choose either the first or second derivative, and then you can choose any of these 3 symbols. Okay, check it out. So along the top we have the 3 possibilities. First derivative is 0, negative, or positive. And then along in the vertical direction we have the 3 possibilities. Second derivative is 0, negative, or positive. And we're just going to go through one by one and figure out what's going on. Okay, the first square, that's where the first derivative is 0 and the second derivative is 0. Oh hey, we just did that. Remember this, table A? These are the possibilities. This is what can happen to the graph when the first and second derivative are both 0. So instead of rewriting that information, I'm just going to say see table A. Okay. You might want to rewind the video for a second and then take a freeze frame there at table A, take a screenshot or something, however you want to keep it for your records. That previous table, table A, is what happens in that case. What happens when the first derivative is negative, but the second derivative is equal to 0? That's a situation where, since the first derivative is negative, it's decreasing the whole time, but the concavity changes. So this is the scenario where you have an inflection point. It changes from concave up to the left of the inflection point. The function is concave up here, this bowl shape, it's curving upwards. And then it changes to concave down to the right. Okay, it's not a critical value, it's not a horizontal tangent line, but it's still an inflection point. It's changing concavity. Let's see, the corresponding thing when the function is increasing is the same kind of shape, but in the other direction. So we'll have a inflection point right there. That's a spot where it's changing concavity. So everything to the left of that inflection point is concave down. It's a downward curving bowl. And everything to the right is concave up. Great. So those are the possibilities for those 2 cases. Now we need to consider where the second derivative is negative, so it'll be concave down, and then we have the different options for the first derivative. Okay, well if the second derivative is negative and the first derivative is 0, we have a critical value, and the second derivative is negative, it's concave down. Now we're just recovering the part of the second derivative test, right? We have a critical value at the point C, and it must be a local maximum because of that concavity. So in this situation, we always have a local maximum. The analogous situation down here at the bottom would be where the second derivative is positive instead of negative, then we'll be concave up. And the first derivative is 0 at this particular point, as we see, so we have a critical value, and that critical value is a local minimum in this case. Okay, so that does it for the first column of the table. Let's move on to the last 4 entries. I know you can't see it at the top, but remember this is first derivative 0, negative, and positive. Okay. So let's fill the other entries in. Let's see, when the second derivative is negative and the first derivative is negative, what does that look like? That means you're decreasing and concave down. So that would be roughly something like this. There's no inflection point, there's no critical values, there's no nothing. You're decreasing and concave down. What about when the second derivative is negative but the first derivative is positive? Well, since the first derivative is positive, you're increasing, but you're still concave down, so that would be a curve like this. Okay, so that's that row. And then what about here? Now we're going to consider where the second derivative is positive, so we'll be concave up. If we're concave up and decreasing, then it's something like this. And if we're concave up but increasing, then it would be something like this. So those are the four possible behaviors depending on the various combinations of the sign of the first and second derivative. Here, let me zoom out and let you see this entire table all at once. Okay. Do you remember way back in the day, it feels like ages ago, many lecturettes ago, we were looking at this table, and we were talking about how the function, the derivative, and the second derivative being positive, negative, or zero affect the shape of the graph? Well, I'd just like to point out that these tables that we just filled out, those are actually telling us about these harder boxes, right? So for example, we considered what happens when the first derivative is 0 and the second derivative is 0. We could be local max, local min, or just inflection points. Depends on the behavior of the first derivative. But the point is that those two conditions, that's exactly the situation where the first derivative is 0 and the second derivative is 0. So that tells us what to do here. I'll say C table A in that case. And then here I'll say C table A and table B. If you look at those various entries in these two sub-tables, that'll tell you what is happening in those cases. It's a little more complicated. Each of those possibilities sort of needs their own table.